So in 1963, Norman Mailer described plastics as new materials cooked in vats, long complex derivatives of urine. So not particularly complimentary about my favourite materials. And a journalist in the New York Times referred to an ocean of oil got by plants manufacturing millions of plastic knives, forks, and so on, littering our parks everywhere. Today, the rhetoric is no less scathing. Plastics are defined or described as an environmental affliction by agencies all over the world. So should the plastics industry be surprised by such bad press? Well, not really, because these are the images that we are confronted with on a daily basis. The general public's perception of plastics and their usefulness, unfortunately, is in a large degree determined by what they see every day, all of this waste. And up to 30% by volume of municipal waste stream is plastic packaging. So it is very, very visible. So it is, without a doubt, it is a serious pollutant. But does it have any advantages? What are the advantages of plastics? Well, first of all, only 4% of the total energy consumed in the world today goes into the creation of all plastic products, and 41% of that goes into packaging. And the other percentages go into construction, automotive, aerospace, and so on. If we were to replace plastics by alternative packaging materials, we would have some very significant and detrimental changes. So the weight of packaging would increase by 400%. The energy required to produce packaging would double, and the overall cost would increase by over 200%. Other benefits include the fact that transportation costs for plastic packaging are significantly less than those for alternative packaging, such as, for example, glass bottles. So by using plastics in packaging products, for example, in the United States, enough energy every year is saved to power a city of 1 million homes for 3.5 years. There's a very direct correlation between the use of packaging and reduction in food losses. And you can see here that in developing countries, we can have up to 50% harvest losses, whereas in our own countries, 2% losses due to good packaging that's available. Automotive applications: for every kilogram of oil used to make plastic for use in automotive, we save 4 kilograms of oil due to efficiencies. This saving leads to a reduction in CO2 of about 30 billion kilograms per year for the EU alone. And show you there are lots and lots of other applications where plastics are so important to our everyday lives, be it in medical, electronics, construction, more and more so in construction, and in a lot of the environmental and alternative energy scenarios that we're looking at require plastics to enable them. So how do we improve sustainability? Well, first of all, the benefits of using plastics are quite clear, but there are very significant problems with over-packaging and also over-design of plastic products, not just packaging, but lots and lots of plastic products. Substantial resource waste also exists in the manufacturing of plastic products. So lots of people are very focused on lightweighting of packaging, but there's a significant amount that can be done in the actual processes that exist to make plastic packaging. And those haven't really changed very much over the last sort of 20 years. So how do we tackle these problems then? So we need to look at the design phase for our products. We need to design for sustainability, which we are most definitely not doing at the minute. We need to look at the manufacturing phase, and currently there are huge savings to be made in the manufacturing phase, very low cost or no cost savings that are not being looked at. And then in the manufacturing phase again, can we identify areas for future improvement? So in the design phase, we need to look at reducing pack sizes, and we need to look at reducing the wall thickness of the packaging. So I'm pretty sure you're familiar with this, the wastage that is involved in packaging, like for crisps, for example, or in the packaging used in that light bulb there. And not only is it wasteful, but it also appears to be very dangerous in some cases to just take the packaging off the product. So we need to reduce unnecessary material in current packaging. We need to introduce new materials with better properties. So an area of research that I work in is on nanocomposites, which can facilitate the reduction of pack sizes and wall thicknesses. And we also need to make greater use of simulation software when we're optimizing our product design. We need to design for recycling as well. So we have lots and lots of plastic products in our homes today that can be recycled, and their properties when they are recycled are very, very good. Unfortunately, the whole supply chain is not set up to fully utilize the benefit of the recyclability of these materials. But just look at the product itself. We have multiple materials, we have different colors, and we also have a product that's very, very difficult to compress for storage. So after 2 days, my recycling bin is filled with plastic containers. So what happens then is the consumer starts putting the plastic into the waste that's just going to be dumped into landfill. So we need to have some clever designs that will enable us to compress these things very readily so that we can put all of our waste into the recycling stream. So current recycling initiatives are not as effective as they could be. There is contamination of the waste stream, for example, by using these colored tops. Now, you know, we don't need to use those. We can think of better ways to do that to differentiate the product. We have bulky packs that fill up recycling bins quickly. We should be using fewer materials, smarter inks and coloring systems, and design features that allow that collapsibility. We also need much, much better supply chain communication in the whole design process. Smarter design is what we should be looking at. And here we have nature's answer to advertising and packaging. At the minute, the original function of packaging, which was containment and preservation, is subordinate, I think, to the marketing function. And we need to get back to the idea that it's preservation and containment that we really need, and look to nature for inspiration. So in the manufacturing phase, there are significant savings to be made. So the UK is one of the top 5 plastic processing countries in Europe. They make a contribution of 2.1% to GDP. Very energy intensive processes. Typical electricity bill is 3 to 5% of turnover. And the industry is dominated by SMEs. So there's about over 7,000 in the UK. And these SMEs, as you have heard from the previous speaker, do not really have the capability to tackle these problems individually. So there are very significant opportunities existing to improve resource efficiency in the manufacturing of plastic products. And they are often no or low-cost solutions. So as an example, I'm going to just look at a case study from an EPSRC project that I led a number of years ago on plastics manufacturing. And I worked with a company that made thermoformed containers that you see here on the right. So they extruded the plastic film, they formed it into the packaging. They were a 24-hour operation going from Monday to Friday. They had 200 employees, £25 million turnover. They were quite a forward-thinking company. And they invested in the latest in technology. And also they had an energy manager and they had an energy policy, which would have, when I went in there, I thought, well, my work's done, I don't have to do anything here. But that wasn't really the case. So in this particular process, we make the sheet of material, it is then fed into the thermoformer, the cups or pots or whatever are stamped out of the plastic. There's quite a substantial amount of waste material you see that's left over, and that's chopped up and put back into the machine again and back into the material stream. What we found was when the main machines were switched off for example, changing over of material or for routine maintenance or for whatever other reason, when the main machines were switched off, the ancillary equipment was left running or idling. So we just looked at that alone and to see what savings we could make there. So we found that, for example, the fans on the printers weren't switched off when the printer wasn't running, the heaters and pumps for the calendar rolls were left running, etc. So we costed the machine, so we found all the machine downtime records, and then we worked out the idling time for all of the ancillary equipment and did a costing of that, what it cost the company to run those machines. And it worked out at £118,000, which was a very, very significant potential saving. It's equivalent to more than £2.36 million in new sales. So when you present the figure to management in those terms, they begin to sit up and listen. There were further unaccounted for costs here. So under no load, the motors have a power factor as low as 0.1. You have increased breakdowns in all of that ancillary equipment that is running needlessly. And also there's a continuous load on the shop floor cooling system. All of those are all additional benefits from switching these machines off. Other areas for potential savings in this particular company, we could have dried the polymer using waste heat, compressed air use in all of the polymer processing plants. It's 10 times the cost of electricity at the point of delivery. So we really need to look at that and optimize its use. And another area that's really astounded me is this whole business of heating up machines. So the company stopped on a Friday, came back to work on a Monday. Somebody came in on a Sunday evening and switched on all of the extruders so that they would be heated up in time for Monday morning work. There was no need for any of, 1 hour heat up time would have been sufficient in this case, but they had them running all night. So the challenges that arose out of this particular work is that companies will devote far more effort to increasing sales or productivity than they will to reducing energy costs, even when they have energy policies and energy managers in-house. Energy costs are viewed as a fixed and necessary evil. One thing we should do is convert resource losses into pounds to get management to act. Culture change is definitely required, and particularly for SMEs, there is a very limited staff resource available in order to affect any kind of change in this particular area. So that is a big, big challenge, and it's already been alluded to in a previous talk. How do we do that effectively? Now, I said that there's lots of potential for improving the manufacturing phase into the future, and most of that, there's a lot of potential in making materials that are lighter, but also the actual processes themselves can be significantly improved. And the one area that I think we should focus a bit more on is that many of these processes have intrinsic waste associated with the process itself. In some cases, this material is recycled. So as I mentioned earlier on, in the thermoforming process, they take the skeletal waste, chop it up, put it back into the process. And they do not consider that there is any waste involved there. But they haven't taken account of the fact that they've already heated that material and cooled it and processed it once. They've got to put it through a granulating machine and the energy that's required to process that and so on. So there is a cost involved in recycling that waste. Also, we have a property reduction, generally speaking, when we recycle our materials. So we need to factor that in. So my view is that we should be minimizing that in so-called intrinsic process waste. So I'm just going to look at a few processes here where there are opportunities to improve. So as in the thermoforming process, there can be up to 30% of your original sheet material can be waste material. And it can be recycled in. But I was in a company recently, and they make the backs of aircraft seating. They pay £30,000 a tonne for this material, and 30% of it is wasted and goes into landfill. And I was just absolutely astounded. But because the material was such a high-value product, it didn't bother them. In injection moulding, in the actual process itself, you have the blue bits there are the parts that you're actually trying to make, and the brown or orange bits are the waste material. So there is a need, and there are some technologies available that will help to reduce, for example, the runners there, but not all companies are using that. And we still have some further challenges there to reduce that intrinsic waste. In all flexible packaging, for example, the material that is used to package your bread bags, the rolls of material have 2 knives put in at the end to slit off little reels of material on either side to make nice even edges for the next process. That could be removed, I believe, by proper control of the width of the actual material coming to the rolls in the first place. So a little bit of investment there could reduce that. And then another intrinsic waste that we have, again, when we're making sheet material, is that we get a phenomenon known as die swell at the end of the sheet. And you have to chop those bits off so that you can run the material through a thermoformer. But it is possible to design your dies in such a way that you can minimize that and then reduce the need to chop that material off. In stretch blow moulding, I mean, you're all familiar with the products made by this process, or fizzy drinks bottles. There's a big push to take more and more weight out of those bottles. And to take 1 single gram out of a bottle requires quite an amount of engineering. And it usually is done by redesigning the bottle to make it stronger, to put in features that will make it stronger if you take some material out of it. There are also initiatives to use better materials. But at the base, if you turn one of those 2-litre bottles over, there's a very heavy bit at the bottom of that bottle that is there because of the process and the fact that the stretch rod is cooling the bottom of the base. And if you took those there's at least 2 grams could come out of that. And that could provide energy for over 700 homes for a year, taking those 2 grams out. In composites, which is an area that I'm just moving into now, there is also quite significant amounts of waste. So you can have up to 30% of top-grade carbon fiber fabric going into the waste stream. And some of it is going right into landfill at the moment. A key issue when we do try and recycle this material is we get a knockdown in the properties of the carbon fiber. So there's a big research opportunity there to try and minimize that knockdown so that we can use the fibers in the original application. But the biggest challenge is to reduce this initial waste in the first instance. In glass fiber composites, it's horrendous the amount of waste that's here. In that product there that you see, the dark green bit is the product and everything else is waste. So approximately 130,000 tonnes of glass reinforced plastic produced in the UK, 67,000 tonnes of waste, mostly going to landfill. So there really needs to be some serious looking at the design of the process and the waste allowables or the design allowables engineers are putting in here. So future research challenges. The use of plastics is going to increase. It's going to increase by about 5% annually worldwide. Much of this is going to be in construction and packaging, but very significant growth now in transportation. Some of the most exciting developments will be in medicine and electronics, and advances that will make our lives much better, such as materials that will be used in patient-specific scaffolds for regenerative medicine. So this is all going to help us, but we really do need to reduce the waste. We need to completely rethink how we design our plastic products. We have to take a systems approach to design and involve all members of the supply chain, and determine the most efficient way to affect culture change in SMEs. That's a big challenge that we should really be looking at. We need to design machines and processes to reduce the intrinsic waste operational losses in material and also in energy and other resources. And this will require a review of all existing machinery, redesign, and possibly design of completely new processes. And finally, we need to look to the natural world to guide us in our design of new products and new processes. So here we have the ultimate process producing the ultimate polymer. It's stronger than steel, it's tougher than any man-made fiber, but most remarkably of all, it is manufactured at close to ambient temperature and pressure, and it uses water as a solvent. So these should be our guiding principles when we look at our new processes and materials. Thank you.